There we go. And we're off. Okay, so Ravenclaw. All right, yeah, there you go. Oh, okay, got it, okay. All right, so as I said, I'm not going to go over the syllabus because the details in terms of the course rules are the same as last semester. So I don't feel the need to take time on that now. You got it, you could read it on your own time, gloriously, all that sort of thing. I handed out the slides that we'll be doing, although first I do want to actually finish up stellar model making. So let's do that, stellar model building, which then it occurs to me I should point the camera more broadly to the board over here, because I forgot I was going to do that. Ugh, off to a horrible start. Well, no, not really, but anyway. Okay, zoom out a little bit. That's in. Alrighty, so we already, did most of this last semester in terms of setting up the equations for static stellar structure and playing around with calculating within a model of pressure and density and all that from one layer to the next, that sort of thing. So let's just, kind of give the big picture overview here, and then we're going to go on and talk about the epsilon, the energy generation rate per kilogram. In particular, it could be gravitational, but it could also be nuclear, and so we're going to do that nuclear stuff in a little bit here. But let's get to stellar model building, the big picture, the grand sweep. Gosh, it would be nice if we could just write down these equations and solve them by hand, but no. You may know by now that, in first year physics, it just looks like I can solve every problem because the textbook gives you problems that you can actually solve, but most problems can't be solved by hand. Most of them, we have to do things like throw a computer at them, so to speak. We have to make numerical approximations. But let's remind ourselves of the equations of static stellar structure. So we had the equation of hydrostatic equilibrium, and here we're assuming that we're making a one-dimensional model. In other words, we just worry about radius and not angle within the star. We just assume everything's spherically symmetric, even though convection really isn't, but we just kind of hand wave around that. So dPdr is minus g m sub r rho over r squared. I hope that rings a bell from last semester. This is saying the pressure gradient is minus g m sub r, where m sub r is the mass interior to radius r, mass within a sphere of radius r, centered on the center of the star, times the local value of the density divided by how far you are from the center, r squared. And so that's hydrostatic equilibrium. Okay, I'll put you on the spot here. I'll write down dm sub r dr is 4 pi r squared rho. This is the equation of What are the in there? It's the equation of It's the equation of mass mass C O, mass continuity, yeah, mass continuity. It's an interesting expression on your face there. Yes, I'm crazy, okay? All right, mass continuity, and then we've got dl sub r dr, luminosity generated interior to radius r, the derivative of that with respect to radius, why that's 4 pi r squared rho. Anybody want to make me super proud and tell me the one factor that's missing here? Epsilon, where epsilon is the, I've already mentioned it. You've just completely forgotten last semester. It's just all gone. The energy generation rate per kilogram. It's how much energy is being generated locally per kilogram within the material. Because 4 pi r squared rho dr would be dm sub r, the little bit of mass in your thin spherical shell. Multiply that by the rate at which energy is being generated per unit mass within that shell. And that's how much you've added to the luminosity in going from r to r plus dr. So we have those three equations. And then we've got the energy transport equations, the ones for dt dr, and remember that's more complicated. It comes in two varieties because energy can be transported outwards by either of two mechanisms. One of them starts with a C, and I'm not conning you, it is convection, yes, convection, and the other is
Radiative diffusion.
yes, radiative diffusion is the other one. Yes, you can have radiative diffusion. So let's write radiative diffusion first. If there's radiative diffusion, we've got dT dr is, I don't even have to tell you this, but it's minus 3 over 4AC times Roscelin mean opacity kappa bar rho over T cubed times L sub r over 4 pi r squared, right? Like I said, you probably were already 2 steps ahead of me as I was writing that out. Wink. So this is radiative diffusion carrying the energy outwards. But on the other hand, there are conditions where convection is the more efficient process and takes over. We talked a lot about that last semester. And in that case, dT dr is, of course, obviously, 1 minus parentheses 1 minus 1 over gamma, which of course you could write as gamma minus 1 over gamma. I don't know why we do it this way. Who knows? Anyway, I could probably think of some reason to. Times mu m sub h divided by Boltzmann, the Boltzmann constant K times G times m sub r over r squared. So this is adiabatic convection. Adiabatic convection. Pressure here. Let's see. What do you remember? What does adiabatic mean for one thing? What's adiabatic mean? If a bubble rises adiabatically, that means there's no what?
Temperature change.
No, the temperature changes. As it rises, it's cooling down. But the question was, does it cool faster or slower than its surroundings? If it cools slower than its surroundings, it stays hotter than its surroundings are and will rise. It'll stay buoyant. So it's not that there's no temperature change, but no something flows into or out of it. No heat. Yeah, there's no heat flow into or out of a parcel if it's rising or sinking adiabatically. So in adiabatic convection, we assume that it is isentropic, it's constant entropy, because no heat, it's on a time scale fast enough that there's no time for heat to flow into or out of the rising and sinking bubbles. So that's adiabatic convection, and this is not the reduced mass. We use this symbol for the reduced mass sometimes, but here it is the You know, it's so nasty. It's not nice. It's the mean. Mean, molecular weight. It's the mean molecular weight. Yes, that is the mean molecular weight. So we've got these 4 equations. I say 4 because it's like 1, 2, 3, 4a and 4b because it's one or the other of these. And then these one are always holding in our model. So we've got those equations. But that's not enough because we don't have enough equations for all of the unknowns we have. So to these, we're going to add what are called the constitutive relations. To these we add the constitutive relations that the pressure is some function of the density, the temperature, and the composition, which we write as x sub j. So the x, capital X sub j, are the mass fractions of the various atomic species. The mass fractions of the various atomic species. So see if you remember the astronomers. So in other words, what we're saying here is the pressure is, we haven't specified what it is at this point, but it's some function. This is saying, if you tell me the local density, the local temperature, and what the gas is made of, I can tell you the pressure. There is some formula that gives the pressure as a function of those local conditions. In the astronomer's periodic table, there's only 3 elements, so to speak. What are their names? So I'll get you started. Capital X represents the hydrogen mass fraction. What percentage by mass is hydrogen? And then there's 2 other things. What are they? Helium, which is capital Y, and then capital Z is metals, meaning it ain't hydrogen, it ain't helium, right? So in other words, we often would just kind of simplify that as P of rho T X Y Z, where that's hydrogen, that's helium is Y, and this is everything else, metals. But if we're really fancy, we might even worry about, well, how much praseodymium is there? How much ytterbium is there? How much, right? But often we just say, X, Y, and then Z is good enough, just the 3 of them. Because how much typically of a star by mass is made of metals, made of everything that ain't hydrogen or helium, roughly speaking? What is it for the sun, roughly speaking? Do you remember? The sun is about what percent metals? Is it 20% or is that too high?
Too high.
Is it 10% or is that too high?
Too high.
5%?
Too high.
4%?
Too high.
Too high, although some stars get that large. 3%?
Too high.
2%? That's about right. 2% is about right for the sun. It's about 2% metals. And hydrogen and helium is everything else. Hydrogen, I think it's like hydrogen is like, what is it? It's like, don't quote me on this. It's like hydrogen is 70%, helium is 28%, and metals are 2%. It's roughly that breakdown. So really then you can often get away with just saying, if I know the total fraction of metals plus hydrogen and helium, I can write a good formula there as far as that's concerned. Aside here, if we assume that it's an ideal gas, if we can get away with that, the pressure would just be rho kT over mu mh plus 1/3 a t to the 4th power. Because remember that rho over mu mh is the number density. So remind yourself of that if you don't. But in other words, this is number density times Boltzmann constant times temperature is one way to write the ideal gas law. So rho kT over mu times mh, mean molecular weight times the mass of a hydrogen atom, is the gas pressure. 1/3 a t to the 4th power is the what other kind of pressure? What else provides pressure in our star? There's the gas. What else? Photons. Radiation pressure. Radiation pressure. So gas plus radiation. So we might be able to get away with that as our constitutive relation as gas pressure rho kT over mu h plus 1/3 AT to the fourth due to radiation, A being the radiation constant, you will recall. And just like me, I'm sure you remember its value. So we got that, and then we assume, and it's generally going to be something very complicated, and in practice a model will have a table of calculated values for specific values of the density and the temperature and so forth, and then you'd use an interpolation scheme to go to other values. But anyway, so kappa bar is some function, right? That's what I'm saying here is some function. I'm not saying what the function is. It's probably something super complicated of the density, the temperature, and the composition. So, and by the way, I should say, when I say x sub j, in other words, it's understood this is really this long list, right, of the mass fraction of hydrogen plus the mass fraction of helium plus the mass fraction of lithium plus the mass fraction of you name it, just all the way down the line. That's what j, in other words, just is an index that runs over all the different, you just numbered the different atomic species. Maybe j is the number of protons. Or if you're just really going to go bonkers, why, you could have it even for every single isotope. Though not typically, you're not going to need that kind of level of detail. And we assume that if we know the gas's pressure, if we know its density, temperature, and composition, that we can do some fancy nuclear physics calculations to figure out how fast the nuclear reactions are generating energy, and we'll have something to say about that shortly. But this is just generically that we say, okay, we assume if we know the density, the temperature, and the composition at any given point within the star, I can calculate the opacity at that point, I can calculate the pressure at that point, I can calculate the nuclear reaction energy generation rate at that point. And as I was alluding to before, unlike this, where I can write a specific formula for it that I might very well get away with, these are generally complicated functions that you really couldn't easily write down. And so they're generally compiled in tabular form on a grid of rho and t for use in computations. You can't write down a specific formula that you just plug into, but you could do detailed calculations for a whole bunch of different rho and t values, and then your value at your local point within the star probably isn't listed in the table, but you can interpolate between known values to get the values at your point of interest. So these are generally compiled in tabular form on a grid of rho and t for use in computations. That is the case with MESA, for example. So in other words, on a grid of rho and t, I mean, okay, imagine there's a rho t plane, right? Imagine your plot. You could imagine making a plot of epsilon as a function of rho and t, so it'll be some surface living above the rho t plane. Again, in general, it's not some function you can easily write down. So what you do instead, imagine that these are all nice and evenly spaced, although even then you might decide not to make them evenly spaced. So for example, MESA that Mac is using in his senior project, and so is ESA, the grid is not necessarily uniformly spaced everywhere, but you can imagine, okay, here's graph paper on the rho t plane. I make graph paper, so to speak, and you calculate those functions at the intersection points of the grid. So you've got this big list of what is epsilon at all those intersection points, all those specific pairs of rho and t values. In general, you might be right here Your value of rho and t might plot right there. It's not one of the ones that was explicitly calculated, but there are techniques for interpolating, for approximating in between the known values to figure out what you should use at your particular location in the star. So, what questions do you have at this point, including, the hell you talking about, Dr. Harmon, or whatever? Could this be any cooler? No, could not. I've answered that question for you right there. Is good stuff, is good stuff. I declare it good stuff, and you are obliged to agree with me. Scribble-do. What is this? It's actually, look, it's a cute little eraser. Look at that. Oh, adorable. I don't think I want to use it on the whole board. Okay. Can I erase all this stuff? Goodbye. Goodbye. Okay, so how many equations did we just write down? A lot, that's correct. The answer is a lot. How many are over there? How many equations? Three equations, right? Those are 3 equations. How many did we write over here before? 4. It was 4 because it's 4a and 4b. So at any given point, there's 4 equations because you're picking the first 3 plus 4a or 4b, right? Which one do you prefer here? Well, the start, right? The physics tells you that. But so in other words, we have 7 equations, right? And if we had 7 unknowns too, we've got a complete set of equations, right? Because in general, you need, n equations if you have n unknowns in order to be able to solve for them are. This is why we need the constitutive relations, because we do, in fact, I'm going to list them, have 7 unknowns, and so we need 7 equations, so those 4 wouldn't be enough. That's why we need the constitutive relations to have 7 equations in 7 unknowns. So we now have 7 equations in 7 unknowns. 7, count them, 7, Right. 1, 2, 3, 4, 5, 6, 7 equations, Well, 1, 2, 3, 4a, 4b, 5, 6, right? Yeah. You all know, by the way, that you have, I've done with this, some of you, this is great for 5-year-olds and it works on adults too. Did you know that you've got 11 fingers? Here, I'll count them. 1, 8, 2, 8, 3, 8, 4, 8, 5, 8, 6, 8, 7, 8, 9, 8, 10, 8, 11, 8. 11 fingers. 1, 8, 2, 8, 3, 8, 4, 8, 5, 8, 6, 8, 7, 8, 9, 8, 10, 8, 11, 8. Hours of fun with 5-year-olds. Okay, so, and I hope you're not like, oh, I can't pay attention now. Figure it out later if you don't know what happened. We now have 7 equations in the 7 unknowns. So there's a movie once, 7 Brides for 7 Brothers, I think, actually. But it's one of those like 50s movies. It's like, crazy things like that. But anyway, in 7 unknowns, 7 equations in the 7 unknowns. Let's list them. There's the pressure. There's m sub r, the mass interior to radius r. L sub r, luminosity generated within radius r. The temperature. The energy generation rate. The Rosslin mean opacity. The density. Those are our 7 unknowns. And we have 7 equations connecting them to one another. In general, no analytic solution is possible. Analytic meaning one you could just write down as a bunch of formulas. I can't write a formula for all of those variables and then you just have to plug in to find it. You have to use numerical integration. But that's absolutely typical. Again, it's absolutely typical. When I was in grad school, one of the fellow grad students, our advisor said that to him and he didn't believe it. He's like, oh, but in classes I've always been able to solve the equations. So my PhD advisor gave him an equation to chew on. A day later he comes back and said, I believe it now. So believe it. In general, we can't just solve these equations. You can't just write down a solution. In general, no analytic solution is possible. So frowny face, oh well, not possible. The equations must be integrated numerically. Numerically. Oh, we can integrate them numerically? Okay, well, we can smile again. And so let's, as you basically already know or should remember or whatever, you can imagine dividing the star up into a bunch of spherical shells, and our job is to figure out the values of all of those 7 variables in each of those spherical shells. So here we are, somewhere in the middle of the star. So there's layers above this, there's layers below this, and of course these layers are just made by the computer. The real star is more like continuous. It's not literally a bunch of shells, but typically your model breaks it into a bunch of shells. I mean, when I'm making star spot models, I break the surface into a bunch of little rectangles. That doesn't mean the star surface is actually a bunch of little rectangles. Okay, and so here I will write that, let's say in this layer, and the dot dot means towards the surface, towards the center, right? There's many layers above and below here. So here we've got shell, we'll call this one here, how many do I want here? I want one more, okay. So this shell in the middle right here, this will be shell I. Up above it, shell I minus 1. Down below it, shell I plus 1. So the implication here is we're calling the surface shell maybe 0 or shell 1, and then we're numbering inwards. We're going towards the center. There are schemes where you would integrate from the center to the surface. There's other schemes where you integrate from the surface to the center. Still others, you integrate from the center and the surface, and you require the solutions to match where they meet up with one another. Kind of like if you build a bridge from both sides of the riverbank, you haven't succeeded unless the 2 halves of the bridge meet at the same level in the middle. There's a cartoon where there's these folks doing that, and the 2 halves come together like this, and they say, can't we at least get partial credit? This cartoon is thought hilarious by professors, as you might imagine, because, of course, students will sometimes ask for partial credit, and as a professor you might be, really? But not always, of course. So just saying. Not trying to be mean or anything. It's just like, it's like, anyway. So let's say that the pressure in this layer is P sub I. P sub I is the pressure in layer I. And here is M sub R comma I, mass interior to this shell, radius I, L sub R comma I, and T sub I, and R sub I, and then I won't list the other ones, but you could, put them as there as well. There's only so much room here. And then down here, why this is Pi plus 1, the pressure in shell I plus 1. M sub R comma I plus 1. L sub R comma I plus 1. T sub I plus 1. R sub I plus 1. And in the shell above it, P sub I minus 1. M sub R comma I minus 1. L sub R comma I minus 1. This is getting monotonous minus 1. R I minus 1. What would the subscripts be in this shell? Just to be sure you're following along. In this shell, all the subscripts instead of I or I minus 1, they'd be I minus 2, and in this one they'd be I plus 2, and so on and so forth, right? Okay? So, given the conditions in shell I, And again, you saw this last semester, but we're reminding, and we're getting the big picture here, because we didn't do this final kind of big picture summary here. Given the conditions in shell I, we could, now in practice this isn't a great way to do it. I'm just going to give a simple Euler integration here. Really the StatStar uses, from the book, uses, some people say Runge-Kutta, but I think it's more like Runga-Kutta or something, you know, to pronounce it. But anyway, we could obtain this, obtain the conditions in shell I plus 1 like so. Why, we could say that the pressure in shell I plus 1 is the pressure in shell I plus the derivative of the pressure with respect to radius evaluated within shell I. How fast is the pressure changing with the radius in shell I times delta R, the change in radius between shells I and I plus 1. Delta R here would be an algebraically negative quantity because we're going inwards here, but doesn't change what you would write for the equation. So this was the simple Euler approximation. We were going over that last semester, right? Where, why is this true? Well, if you subtract, this is saying that pi plus 1 minus p sub I over delta R, well, that's the change in P divided by the change in R, is approximately dP dr, right? In other words, this is just the approximation to the derivative that we're making there. We're approximating the derivative with a finite difference. Here, delta R is Ri plus 1 minus Ri, and if indeed we're numbering where it's increasing inwards, it's less than 0 in this case. If we were going the other direction, it'd be greater than 0. So if I know the conditions in shell I can get the conditions in shell I plus 1, and do that for all the variables, and then use those to get the conditions in shell I plus 2, and then use those to get the conditions in shell I plus 3, and so forth. So you can imagine marching inwards. You know the conditions in some particular shell. You can keep marching inwards to get the conditions in all the other shells. So that's the basic idea with a numerical model like this. It's always going to be an approximation because derivatives are defined at points. And so we're making a finite difference approximation to what we would really model as continuous variation within the star. But as long as the shells are thin enough and blah, 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 we expect to be able to get a good approximation to what the actual solution would look like if we could somehow manage to write it down. So we would find the shell, the value MRI plus 1. Why, that would be equal to MR comma I plus, just to be sure you're following, what am I going to write right here? It's MRI plus, what derivative? dMRI dr, right? dMRI dr times, and evaluated in shell I, times delta R. And also, to be sure you're following, how do I know what dP dr is? How do I know what that derivative actually is? Do we have an equation which tells us what that derivative actually is? And if so, what is that equation? Did we write down an equation for dP dr? Yeah, what was it? Yeah, the equation of hydrostatic equilibrium, right? In other words, we have an equation for that. dP dr was minus g m sub r rho over r squared. So we would put in for all the shells. So we have a way to figure out what this is, right? And so from the equation of hydrostatic equilibrium, we can find out what the pressure in shell I plus 1 is once we know what the pressure in shell I is, et cetera, et cetera. And similarly here, why do we have an equation which tells us what dmRI dr is, what the derivative of mass with respect to, actually I would just say dm sub r dr, evaluated for shell I. Why do we have an equation which tells us what dm dr is? We do. dm sub r dr is equal to, what is it? It's equal to, what is it? What is it? It's in your notes. Yeah, 4 pi r squared rho, right? 4 pi r squared rho. So that's the point, is those equations that we've written down for, this equilibrium and that, this and the other thing, they let us evaluate these derivatives so that we can step through the star. So, and similarly, for L sub r I plus 1 and T sub r I plus 1. Because the third and fourth equations, 4a, 4b, the third and fourth equations told us the luminosity derivative and the temperature derivative. So we can write similar equations for those to let us keep stepping through the star. And so, glorious, we can do this. And once we've used those equations which tell us those important derivatives, we can use the constitutive relations to get the other variables. The values of rho I plus 1, kappa bar I plus 1, and epsilon I plus 1 are then obtained using the constitutive relations. So we have found all 7 variables. We've been able to find all 7 variables in shell I plus 1 if we know what they are in shell I. And we can just keep doing that over and over again. Now we're ready to move on to shell I plus 2. So in principle, we can go all the way to the center of the star. And this kind of makes it sound like, oh, no problem. But what we haven't talked about yet is boundary conditions. Because if you don't start with the right values at the surface, you'll know, because what will happen, for example, is you'll integrate inwards and you'll discover, whoops, my star is hollow in the middle. Or, whoops, the other boundary conditions are not met. And so only the point here is that, and you've seen this before, but you may not have fully cogitated it. It's similar in quantum mechanics. So anybody who takes quantum mechanics from me has to learn the following mantra. It's the boundary conditions that put the quantum into quantum mechanics. Because you can solve the Schrodinger equation in the infinite square well, for example, for any energy whatsoever. You can come up with an equation, you can come up with a psi for any energy you like, but in general it won't satisfy the boundary conditions. It won't go to 0 on the 2 ends of the well. Only solutions that satisfy the boundary condition that psi is 0 on the 2 ends of your infinite square well are legitimate, keepable solutions of the Schrodinger equation. There's a solution for every energy, but only the ones that satisfy the boundary conditions are allowed, and so the energy quantization does not come from the Schrodinger equation by itself. It comes from needing to satisfy the boundary conditions. And the same is true for our star. You can come up with an infinite number of solutions, but only the one that satisfies the boundary conditions for your star is the right one, and that's the point. So I'm going to keep saying that here, but I just wanted to kind of show that, say that beforehand. What questions do you have at this point? Okay, so I will throw in that, as I mentioned, in practice, more sophisticated integration schemes like Runge-Kutta are used instead of the simpler Euler method used here. Nobody would actually use the Euler method to really do these calculations. It's not accurate enough. In practice, more sophisticated integration schemes like fourth order Runge-Kutta are used rather than the simple Euler method described here. Here. Why, that's not going to be good enough, but in principle, right, it helps us understand what's going on. But the solution must not only be satisfy the 7 equations, there's an infinite number of solutions. I can specify arbitrary values in any given shell and come up with a solution. There's an infinite number of them, but it must not only satisfy the 7 equations, but also the boundary conditions. And again, I can't emphasize how important that is. I don't think when I was an undergrad I fully understood how important it is. So I'm trying to fix that with you, is to get you to understand just how fundamental that is. But also the boundary conditions. So those would be m sub r goes to 0 and L sub r goes to 0, both of them as r goes to 0, right? So remember, here's our star, here's some spherical surface with radius r in there, and remember that m sub r is the mass interior to radius r. So why should the function m sub r become 0 when r becomes 0? Why is m sub r for r equals 0 equal to 0? Why physically does that have to be true? And it's not particularly profound. So why should the mass interior to radius r go to 0 when r goes to 0? Yes?
Because as the radius approaches 0, there's nothing contained in it.
Correct. If you go to 0 radius, there's nothing to contain the mass anymore, right? So the mass interior to a radius of 0 should be 0. Now, that's obvious physically, but the equations don't know that. It's not hard at all to solve the equations and find that m sub r is 42 million kilograms at r equals 0. So somehow miraculously, in that point at the center, there are 42 million kilograms. The math can certainly do that. You could integrate inwards. You could say m sub r for some particular shell. You follow this prescription. You go in and in and in and in, and you get to r equals 0, and it gives you a value of m sub r. That is not 0. It's a solution of the differential equations, but it doesn't satisfy the physical boundary condition. The math doesn't know this, but it doesn't satisfy the physical boundary condition that the mass interior to 0 radius better frickin' well be 0. Does that make sense? You see what I'm getting at there? Now, either that, or you've got a singularity at the center of the star, right? A point of infinite density. But we figure that's probably not very likely that our star has a naked singularity in the center. And so we throw solutions like that out. That's the idea here. You could have a delta function of density at the center. Mathematically, you could have, a point of 0 size but finite mass there. But what would that be? That's not a thing. And so this condition is a physical imposition. The math, the equations themselves don't know this, but we say this has to be true physically. And so that constrains the solutions. Why should L sub r, the luminosity generated within radius r, go to 0 as r goes to 0? Kind of similar reasoning. Why should L sub r, the luminosity generated inside radius r, go to 0 when radius r goes to 0 so that it's only the point at the center of the star? Why should that be? Yes?
There would be no particles like...
Yeah, there's nothing inside there to be making energy, and so therefore there can't have been any luminosity already there at the center, because there's nothing closer to the center than the center to be producing luminosity. So both these conditions should hold, and so our solutions are only valid if they meet this boundary condition. You make your solution, there's an infinite number of solutions that don't meet these boundary conditions, but only the ones that do could be legit. And again, I'll say similarly with a situation that you might have seen more often is, remember the infinite square well from quantum mechanics, right? What do the wave functions look like? They are they are, sketch me in the air the wave functions inside the infinite square well. Yeah, woo, right? Sinusoids, right? Trigonometric functions, right? So the wavelength of the sinusoid is related to its energy. There is a solution of the Schrödinger equation that within the well would look like this. That's a sinusoidal function. It would be energy of h bar squared k squared over 2m, where k is 2 pi over the wavelength. Is this a legitimate equation? This is a solution of the Schrödinger equation. The solution of the Schrödinger equation inside the well is any sinusoid is the solution of the Schrödinger equation inside the well. Is it an allowed solution? What's the boundary conditions? What does the wave function have to do on the edges of the infinite square well? It has to be equal to 0 on the edges, because the wave function, you may recall, it's 0 outside the well, and it has to match up at the boundaries. So this satisfies the Schrödinger equation, but not the boundary condition that psi has to be 0 at the two edges of the well. And so that means that the only allowed solutions are these guys, right? There's the one hump solution, so to speak, and the 2 hump solution, and the 3 hump solution, and so forth. All those discrete solutions with different energies, those arise not from the Schrödinger equation itself. every energy is a solution inside the well, but only these specific solutions meet the boundary conditions and therefore are allowed solutions. So therefore, it's the boundary conditions that put the quantum into quantum mechanics is what I'm saying there. And similarly with our solutions for our star, there's an infinite number of solutions, but as we'll see, only one of them is going to meet the boundary conditions at both the center and the surface, and that picks out a unique structure for the star, is what it comes down to. That makes it that there's only one actual solution for the star itself. More on that after the break. Did you say you wanted more boundary conditions? Well, you are in luck. We're going to throw some more boundary conditions up here. All right. Because we've only put boundary conditions for 2 of our variables, and we've got 7 of them. So additional boundary conditions, additional BCs. So this one will just be an approximation. We're going to say that these are all going to be as R goes to R star, where this is the radius of the star. Now you might be, well, how do we know that? Well, for now, just imagine we've observed the star's radius. We're doing this for the sun. We know how big the sun is. It can get complicated if you don't have some already independent estimate of that. But in any case, the pressure goes to 0 at the surface of the star. The density goes to 0 at the surface of the star. The luminosity, by the time you're at the surface, should be the star's entire luminosity, L sub r. At the surface, you're at R star, well, then that should say that all the luminosity has been generated at that point, and you've just got the star's luminosity. Similarly, M sub r should just go to the whole mass, the actual mass of the star. Once you're at the surface, you've included all of this, all of it. Now again, subtle points are like, well, stars don't have a super well-defined surface. They just kind of fade away. They're gas balls. But it is true, you get to a point where there ain't much above that. So there's some fuzziness here, as it were, just like stars themselves are fuzzy. But for purposes of discussion, we'll just say there's some well-defined stellar radius, and, well, the sun's core temperature is like, is like 15 million Kelvin. Its surface temperature, as you'll recall, what's the photosphere's temperature roughly? Do you remember? Starts with a 5. 5,770 Kelvin, yeah, like 5,800 Kelvin, 57, 77, or something like that, right? Is that comparable to 15 million Kelvin at the center? No, it is not. So in other words, compared to the central temperature, by the time you're at the surface, why, you've practically cooled off to 0, but of course that's not really true, so we'll add in here that actually T does not truly go to 0. Actually, T goes to 0 as R goes to R star is not strictly true. And if you're trying to, make professional level stellar models, you got to do better than this. But StatStar, the model in the book, which is, kind of for teaching purposes, StatStar uses this as a simplifying assumption. I love me some Hagoromo chalk, but I'm not too fond of the way it's so crumbly. But it goes with how nicely it writes otherwise, so I guess you got to take the good and the bad. StatStar makes it, where am I? StatStar, where are we? Uses this as a simplifying assumption. So our solutions for all the different variables have to satisfy all the boundary conditions that are imposed by physicality, as it were, by the physics. And what we will generally find is if you start out with some set of values at the surface and integrate inwards, like we were talking about here, you get to the center and L sub r and M sub r aren't 0 at the center, and so it's womp womp, can't take that solution. Now, when you're doing a numerical solution, you would have some convergence criterion, right? In other words, if it were close enough to 0, you'd say, okay, our solution is close enough to being right. But in practice, I mean, in principle, there'd be only one true solution that exactly met those boundary conditions. So, if we start at the surface, we imagine providing known values at the surface and integrate inwards, for assumed specified values of stellar luminosity, stellar mass, radius of the star. We generally find that the solution does not satisfy the boundary conditions at the center. So you can always find a solution. You give an arbitrary assumed luminosity, mass, and radius. You can arbitrarily specify those, integrate inwards till you get to r equals 0, and in general, you've got a solution, but it doesn't satisfy the boundary conditions at the center. We generally find that the corresponding solution, which won't be an allowed solution because of this, the corresponding solution, it satisfies the equations but not the BCs, the corresponding solution does not satisfy the boundary conditions at the center. In other words, M sub r doesn't go to 0, L sub r doesn't go to 0. Does not satisfy the BCs at the center. Namely that M sub r should go to 0 and L sub r should go to 0 as r goes to 0. So you reject such a solution. And what you can imagine is you keep trying different values, different combinations of L star, M star, R star, until you hit the magic combination where the solution does satisfy the central boundary conditions, and you say, aha, that must be what the actual mass, luminosity, and radius of the star are, according to my model. So, at this point, what questions do you have? Yes, yes, yes.
What's the word after integrate?
Let's see. Integrate inwards. Inwards, yes. Yes, integrate inwards. Integrate blah, blah, blah. Inwards, yes. Integrate inwards. Okay, any other questions? Okay. Given M star, the mass that you want to make your stellar model, you might say that's fixed. I'm modeling a 1 solar mass star. I'm modeling a 0.7 solar mass star, whatever you might say. I'm going to keep that fixed and try different values of that I assume of what its luminosity and radius are and see what I can get away with. Given M star and the composition and the x sub j values, given the mass and the composition, we find that only for a specific unique pair of values of L star and R star, only for a unique, there's only one, specific pair of values of L star and R star, by which I mean there's one L star and one R star that work and no other values. Does the solution satisfy only for a unique specific pair of values of L star and R star? Does the solution satisfy the boundary conditions? Any other combination of L star and R star that you try, it doesn't satisfy the boundary conditions at the center. And similarly, one finds, similarly, if we say M star, R star, and L star are all specified, only one composition works. If we say, I know the mass, luminosity, and radius of my model, and I keep varying the composition till I get the solution to work to satisfy the BCs, a unique set of X sub j is required. Only one composition works. And this leads us to the glorious final conclusion here that I alluded to before the break. These considerations and similar ones for full time-dependent models, because remember, we're making these static models, they don't evolve in time, but if you want to be more sophisticated, you allow the quantities to vary with time. So these considerations and similar ones for a time-dependent case lead to a uniqueness theorem. Similar ones for the time-dependent case, where we let our model change over time. Why it leads to one of the most important results in astrophysics, lead to the Vogt-Russell theorem. The Vogt-Russell theorem says the mass and composition of a star uniquely determine its radius, luminosity, and internal structure, as well as its subsequent evolution. It's a little bit of a lie, because there's also some dependence on its overall angular momentum, for example, magnetic field, and so forth. But overwhelmingly, the most important things you need to know about a star are what's its mass and what's its composition, and that essentially tells you everything about it. It tells you the whole story of the star, except for some small details. If a star is spinning faster, that makes a little bit of a difference, and so forth. But the mass and composition of a star uniquely determine, again, that's a little bit of a lie, because the angular momentum does play a small role, but these are overwhelmingly the most important factors, mass and composition. Uniquely determine, so asterisk, okay, almost uniquely, leave me alone. Uniquely determine its radius, luminosity, and internal structure. And also its subsequent evolution, like how long it's going to live, and so on and so forth. It's all deterministic. It's like, tell me these things and I can tell you the star's entire life history. Radius, luminosity, and internal structure. And as well as its subsequent evolution, its life story, its fated, its destiny. Oh, I haven't said life story. Subsequent evolution, I meant to say. Life story is a little more, I don't know, fanciful. And its subsequent evolution, but that is its life story. Subsequent evolution. So in other words, you could imagine, at least in your head, here's two stars and they're both one solar mass, but one of them has twice the luminosity of the other when they're the same age. And this says, nope, no, 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 no. If you had another one solar mass star just like the sun, they'll essentially behave identically to one another. They'll be twinsies in every way. Now again, details. The angular momentum determines things like how strong the magnetic field will tend to get and stuff like that. So one might be more magnetically active if it started out with more angular momentum. But it's not going to affect big picture things like how long it spends on the main sequence and all that sort of thing, how long it fuses hydrogen in a shell. Tell me the mass, tell me the composition, and I'll tell you everything you want to know about that star, is what the Vogt-Russell theorem says. Again, almost everything. Details, but essentially just about everything important about the star. I hope you can appreciate how important that is. It's just like, you know, that's just saying that, okay, we know what controls stars, essentially. It's their mass and their composition. What questions do you have? Shall we make us some nuclear energy? Yeah, let's make some nuclear energy, shall we? So, to start with, this is a very important plot right here. So this is the binding energy per nucleon, so per proton and neutron within the nucleus, because, as you may know, if I have, for example, 4 protons, I can fuse them together to make a helium-4 nucleus, and the mass of that helium-4 nucleus will be about 0.7% less than the mass of the 4 protons that fused in order to form it. And that's the key to powering our star, because the missing mass shows up as energy by which the star shines while it's on the main sequence, the fusion of hydrogen into helium, because the helium has less mass than the 4 hydrogens that went into it. And I need to turn the camera this way, it occurs to me. So let me do that for the audience at home, those who are keeping score at home. So let's get that over there. Okay. And so we can cast that in terms of the binding energy per nucleus, per nucleon. In other words, because there's potential energy of interaction between the protons and neutrons, the strong nuclear force binds them together, attracts them together. That negative binding energy, because E equals mc squared, mass and energy have equivalence in relativity, that negative binding energy shows up as a reduction in the mass of the particle. And so this is a plot of the binding energy per nucleon, which means, in other words, if you separated all the protons and neutrons from one another and added up their mass, and then you combine them, if you imagine you could somehow combine them all at once to produce the nucleus in question, the binding energy is that divided by c squared is how much less massive the nucleus is than all the particles that are used to assemble it, all the protons and neutrons that were used to assemble it. And what we find is that the plot of binding energy per nucleon looks like this, and in particular, of all nuclear species, iron 56, 26 protons and 30 neutrons, has the highest binding energy per nucleus. It's the most per nucleon. It's the most tightly bound nucleus. And what that means is that if you fuse something with iron 56, you go up the curve. If you fuse anything with iron 56, the result has more mass than the iron 56 nucleus plus whatever fused with it, which means you don't get energy out in that case. You have to turn energy into mass. And so iron 56 cannot serve as a nuclear fuel in terms of fusion, because if you bind anything with it, the result has more mass than you started with, so energy had to be converted to mass instead of the other way around. And similarly, if you made iron 56 break apart, the resulting nuclei would have more mass than the original iron 56 nucleus did, and so that would take energy. It would be an endothermic reaction instead of an exothermic reaction. You'd have to put energy in order to make it happen. So iron 56, we'll see later, when the core of a star becomes made of iron 56, it's doomed because it's out of nuclear fuels. It can't fuse to help keep supporting the star. But on the other hand, nuclei which are less massive, lower down, basically smaller mass numbers than iron 56, with them, if you fuse them, you get energy out. And so, for example, there's hydrogen up there, and here's helium down here. Notice that's the biggest gap. If you fuse hydrogen into helium, you get about 0.7% of the mass of the original hydrogen out as energy. And similarly, if you fuse helium into carbon, the carbon nucleus has less mass than the 3 helium-4 nuclei that went into forming it. And so you get energy out as a result of that. Do you get as much out as you did by fusing hydrogen into helium? Here's helium into carbon. There's hydrogen into helium. Which one's giving you more energy out per nucleon involved? By far, it's the fusion of hydrogen, right? So someday the sun will fuse helium into carbon, but there's not as much of available energy when you're fusing helium into carbon, so that's not going to last as long as the fusion of hydrogen is. Helium's not as good a nuclear fuel as hydrogen is, because you don't get as much out per kilogram of helium that you put into the nuclear reactions as you do from hydrogen. And so anything less massive than iron, you can get energy out in principle by fusing it with other stuff. Anything more massive, you can get energy out by fission, by splitting apart. So this is the key to nuclear power plants that run on uranium or plutonium isotopes that are unstable. They can undergo fission, move down the curve, and the fission products have less mass than the original nucleus did, so energy comes out. But iron is the bottom of that curve. So beyond iron, you can get energy out via fission. Below iron, you can get energy out by fusion. And iron's like, nope, I'm sorry. You're not using me for a fuel. I'm just going to collapse into a neutron star or a black hole instead, as we will see. Okay, so that's kind of the big picture here. Okay, any questions about that? Okay, now, another important fact is hydrogen is not fusing into helium in this room, even though there's plenty of hydrogen nuclei in this room. You've got plenty of hydrogen nuclei inside your body. They're not fusing into helium nuclei. This is probably a good thing, because while so-called cold fusion, which for a while people thought they'd actually discovered, would be a great source of energy, you wouldn't want your hydrogen to be fusing into helium in the end. So why not? Why doesn't hydrogen just fuse into helium at room temperature? And the answer is, let's see, A hydrogen nucleus, the simplest kind of hydrogen nuclei, is a proton. Protons have what kind of positive, what kind of positive charge do protons have on them? The positive kind, yes. What about neutrons? They're uncharged, right? That's why they're called neutrons, they're neutral. If you have two protons flying towards one another, are they attracting one another or repelling one another? They're repelling because of the Coulomb interaction, right? And so if they're not moving fast enough, they will veer off course before they can collide and stick, so to speak. And so at low temperatures, they don't collide and stick, they don't fuse with one another, but at high enough temperatures, you can get the first step of the so-called proton-proton chain that generates most of the sun's energy, where a proton can collide with another proton and stick, so to speak. And we'll see later, next class, that this requires quantum tunneling, that this quantum mechanical phenomenon of tunneling through a potential barrier that classically you wouldn't have enough energy to get through allows this to happen at temperatures of about 10 million Kelvin, whereas without that it would take temperatures of like 1 trillion Kelvin, and we'd be living in a very different universe. In fact, we wouldn't be living in the universe because we wouldn't have a star making nice energy for us, et cetera, et cetera. So thank you, quantum tunneling, for allowing us to exist, and talk about how quantum tunneling allows us to exist, kind of meta there. But in any case, suffice it to say, high enough energies, they can be moving fast enough that they collide and stick, if you will, before they would veer off course with one another. So clearly, let's see, what corresponds to how fast things are moving around on the atomic level? What property of a substance tells you how fast the little the microscopic particles are moving around? Why, that's its temperature, right? So fusion requires high enough temperatures, is what it comes down to, because things have to be moving fast enough to overcome their electrical repulsion and fuse. And what happens is that one of the protons turns into a neutron by spitting out a positron and a neutrino. Okay, we'll get back to this when we talk about quantum tunneling and so forth, but let's look at the reactions that generate energy inside the sun, the fusion of hydrogen into helium. So here we have the PP1 chain, the proton-proton 1 chain. And I memorized it when I was like in 7th or 8th grade because I was me. I don't know if any of you have memorized it at this point yet. But because I was me, I decided to memorize it. So I got this down. We'll write it out all fancy in terms of like, like kind of equation style here. But here's the picture. So it starts when a proton fuses with another proton, and then it goes bang. Okay, that's just a cartoon illustration. Out comes a positron and a neutrino and a deuteron. A deuteron is a deuterium nucleus. It's a heavy hydrogen with a proton and a neutron, because remember, everything that has one proton is hydrogen, everything that has two protons is helium, but you have different isotopes, different number of neutrons. So let's talk about hydrogen fusion reactions, and we'll be looking at the picture at the same time we put down the kind of equation notation on the board here. Hydrogen fusion reactions. So, the predominant reaction is the first proton-proton chain in the sun's core. Predominant reaction in the sun's core is the first proton-proton chain. if you've taken Astronomy 111, I just said the proton-proton chain. I never said the first proton-proton chain, because it turns out there's also pp2 and pp3, Roman numeral 2, Roman numeral 3, that also contribute. pp2 is actually a fair amount, is the first proton-proton chain. First proton-proton chain, which would get tiresome to keep saying all the time. And so it gets abbreviated as capital P, Roman numeral 1, proton-proton 1. It's named for the fact that it starts when two protons collide with one another. So, in designating nuclear species, we use this notation just to get ourselves on the same page here. So we've got capital A, capital Z, giant capital X. So X equals the chemical symbol. So for example, there might be a big H here, or an HE, or a C, or whatever. It's the chemical species designation there. X is the chemical symbol of the nucleus involved. A is the mass number. It's the mass number equals, what's the mass number? Do you remember? What's the mass number of a nucleus? So for example, for helium-4, 4 is the mass number. So it's the total number of, it's the total number, protons plus neutrons. It's the total number of nucleons. So equals number of protons plus number of neutrons. And Z, capital Z, is the atomic number. Atomic number for hydrogen is 1. The atomic number for helium is 2. The atomic number for lithium is 3. The atomic number is the number of what? Yeah, just the number of protons, right? The atomic number is the number of protons, and remember, that's what decides what kind of nucleus is. It is atomic number equals number of protons. The thing that tells you what kind of nucleus it is. Every helium nucleus has atomic number 2. I'm sorry, atomic number 2. Every carbon nucleus has atomic number, how many protons in a carbon nucleus? That's nitrogen. 6 for carbon, 7 for nitrogen. How about oxygen? That's 8. That's 8, yeah, et cetera, et cetera. Okay. All right. So, hey, people following along at home, just be sure to remember this because I'm going to show more of the board now. Actually, I'll just zoom out a lot and that'll still be there on the side looking cute and tiny and all. Looking so adorable over there. Look at those adorable nuclear fusion reactions. Oh my God. I just love them. Yeah, doesn't quite all fit, but good enough. Anyway, yeah, I'll go like to here. How far is that? Okay. All right. So with that notation, here's the PP1 chain in all of its glorious gloriosity. Because the only kind of gloriosity worth having is glorious gloriosity. So, with this notation, the PP1 chain is, so it starts with 11H. What is that? What is that thing? What is a 11H? So it is a nucleus that has how many total particles in it? 1. How many of those particles are protons? 1. Therefore, it is a hydrogen. It is a proton. 11H is a proton. It's a bare hydrogen nucleus. There are hydrogen nuclei with 2 and with 1 and 2 neutrons in them as well. But that's a bare proton right there. That's a proton plus another proton. Right? So this is proton plus proton becomes 2,1H plus E plus nu sub E. So we need to say some more about all that. What is 2,1H? How many protons are in this nucleus? How many protons are in this nucleus? 1, that's the bottom number. How many total particles are in this nucleus? 2. So how many neutrons are in this nucleus? 1. So this is a nucleus with 1 proton and 1 neutron. It is therefore what chemical element? What chemical element has 1 proton in the nucleus no matter how many neutrons? Hydrogen. So it's hydrogen, but it's quote-unquote heavy hydrogen because of that extra neutron. What do we call heavy hydrogen? Starts with a D? Deuterium, right? So this is a deuterium nucleus, also known as a deuteron. That's a deuteron, 2,1H, plus, what's an E plus? It's the opposite, so to speak, of an E minus. What's an E minus? That's an electron. So what's this? That's a positron, an antimatter electron, plus positron plus electron type neutrino. Electron type neutrino. So E plus equals a positron as opposed to E minus is an electron. So I'm going to teach you all a little bit of nuclear physics and conservation numbers and all this kind of stuff, or I mean conserved numbers and so forth. Nu sub E is an electron type neutrino. Neutrinos are, we used to think they were massless. Now we know that they are very low mass but not massless. They are particles that only interact via gravity and the weak nuclear force. And so we think that dark matter in the universe might be sort of a heavy version of a neutrino, not a neutrino, but something that similarly only interacts via gravity and the weak nuclear force. They have very low masses and are created with high enough energies in nuclear reactions that they're generally going to be moving relativistically. And because they only interact via the weak nuclear force, they are very hard to stop. A neutrino could go through a light year of lead without interacting with anything. There are literally trillions of neutrinos passing through your body every second. If they deposited their energy, it would kill you instantly. There's enough energy in those neutrinos that it would kill you, but they don't interact with other types of matter very much at all, and so they're just constantly passing through all the time. Thank goodness for that. And most of them are left over from the Big Bang, as a matter of fact. But then they've also got a continuous stream of neutrinos from the sun. And it turns out, as we'll see, when a star goes supernova, when a massive star undergoes a core collapse and produces a supernova, more energy comes out in the form of neutrinos than in the form of anything else, as we will see. And we confirmed that they release neutrinos when in 1987, a neutrino detector near Cleveland picked up, I think it was 12 neutrinos just all at once, unexpectedly, and those were the harbinger of the explosion of supernova 1987A in one of the Magellanic Clouds. And we saw those a little bit before we saw the supernova itself, and that's predicted that we would see the neutrinos before we saw the rest of the explosion, which was a beautiful confirmation of the idea that we understand what's going on. Okay, so meanwhile, I meant to put this on the right of each of these reactions here. So you might decide to do that, or you could put it on the left or whatever. I'm going to say mean reaction time per nucleus. In other words, how long does a typical proton last before it combines with another proton like this? And the answer is, on average in the sun, in the sun's core, on average 7 billion years. Typically, it takes 7 billion years before any given proton in the sun's core, on average, combines with another proton to make a deuterium nucleus. How old is the sun? 4.56 billion years old. This means every single proton that has ever fused in the sun has beaten the average. Because on average, it takes 7 billion years before a proton fuses with another proton. But it's only an average. But because the sun isn't 7 billion years old yet, every single proton that has ever fused in the sun so far has beaten the average. It did it early. If you consider hitting another proton and forming a deuterium to be like a life goal, they're all early achievers. They're precocious protons, as it were. You know what? I just decided if I ever made a rock band, it would be called Precocious Protons. There we go. That's my future rock band. I'll license the name if anybody else wants it. Okay, 7 billion years. We'll say more about conservation laws involved with this probably next class. But so just as a precursor here, leptons, which neutrinos and electrons are, have what is called lepton number. And in particular, electrons and positrons have electron-lepton number, and electron-type neutrinos also have electron-lepton number, and an electron has L sub e, capital L sub e, electron-lepton number plus 1, and a positron has L sub e equals minus 1, and an electron-type neutrino has L sub e equals plus 1, and an electron type antineutrino has L sub e equals minus 1, and electron-lepton number is a conserved quantity. It's the same before and after an interaction. I'll write all this down next time, but I'm giving you a little foretaste today. Are there any leptons on this side of the equation? Are there any electrons and neutrinos on this side? No. So what's the total electron-lepton number on this side of the arrow? 0, because there ain't no electron or neutrino type leptons. 0. On this side, what's the electron-lepton number of the positron? And I have you do this in a homework where you fill in blanks in some reactions by saying, oh, I have to conserve all these. Yeah. This one is not plus 1 because we consider the matter ones to be the one with plus 1. So the positron has electron-lepton number of, I know you can't deduce it just from thin air, you have to remember what I said. This one has L sub e, I'll just decorate this. This has L sub e equals minus 1. How about the neutrino here, this electron neutrino? It's a matter particle, not an antimatter particle, so its electron-lepton number is plus 1. So leptons that are particles have plus 1 as the lepton number. Leptons that are antiparticles have minus 1, which is arbitrarily assigned, right? In other words, you just have to be consistent. Just like we could have said protons were negatively charged and electrons were positive. We could have said that. You just have to pick a thing and be consistent with it. In fact, you all know XKCD, the comic, right? You ever saw the one where time travelers come back and they're trying to get Ben Franklin to decide the opposite convention he had for like when you rub amber with fur or whatever, because electrons should, I forget which one gets positive and which one gets negative charge, but he picked the wrong convention, which is why electrons are considered negatively charged. Why should we have made electrons be called positively charged? What would make it a little more convenient if we did that? What actually flows in circuits? electrons. So when we draw current, we do it in the direction of positive charge flow, which means the electrons are going the opposite direction of the current arrow, right? So if we had to do it again, we would make electrons positively charged so that current arrows and the charge carriers would be moving in the same direction. But it's too late now. The convention has already been decided. Proton should have been negative, electron should have been positive. It's too late. So, I mean, we could fix it, but there'd be a disaster, all the other things. So what's the total electron-lepton number on this side? Why do you keep saying electron-lepton number? Because muons and antimuons and muon-type neutrinos and anti-muon-type neutrinos have muon-lepton number. And there's finally tauon-lepton number. There are 3 generations of leptons and quarks. And so there's 3 types of lepton number. And the stable ones are electrons and their electrons, positrons, and their corresponding antiparticles. So what's the total lepton number on the right-hand side of the arrow? It's 0. So have we conserved lepton number? We did. In other words, if I tell you this is a positron, that there's a positron emitted, there has to be an electron-type neutrino emitted as well in order to conserve the lepton number. And so this allows you to deduce things about the reactions. Meanwhile, is electric charge conserved? Did you take E&M? Is electric charge overall conserved? Yes, right? What's the total charge over here in units of the charge on a proton or an electron, if you consider just a positive quantity? What's the total charge over here? If you call 1 the charge on a proton, what's the total charge over here? +2, right? What's the total charge over on this side? +2, right? Because 1 + 1 is 2. So electric charge is conserved, lepton number is conserved, so is baryon number. Protons and neutrons have baryon number, +1, both of them. And how many, that essentially means that the total number of baryons minus the total number of antibaryons is the same on both sides of a reaction. How many baryons, protons or neutrons, are on this side of the reaction? 2, right? Proton and a proton. How many baryons are in this side of the reaction? Where a baryon is a proton or a neutron. And an antibaryon is an antiproton or an antineutron. How many baryons over here? 2, because this is a proton and a neutron. So we've conserved baryon number, we've conserved electric charge, we've conserved electron number. The homework that it's already been posted, it gives you these nuclear reactions, and you have to fill in some blanks knowing that you have to conserve charge, baryon number, and lepton number. That's how you can do that. Okay? All right. So the next step is that the deuteron collides with a proton to form helium-3. In other words, 2 protons and a neutron. It's helium because it's 2 protons. It's helium-3 because it's 1, 2, 3 particles instead of the more common helium-4 with 2 protons and 2 neutrons. So you get helium-3 as an intermediate stage here. Deuterons have a much higher reaction cross-section than protons do. It's much easier to fuse deuterons because of complicated nuclear physics reasons. And so you can fuse deuterium at a much lower temperature than you can fuse protons with one another. And this means that, as Cecilia Payne-Gaposchkin said, deuterium is stellar baby food. In other words, it's the first thing they fuse because it requires lower temperatures than the fusion of regular hydrogen like this. And so deuterium is the Gerber of stars. Meanwhile, there are objects called brown dwarfs. You might have heard of them before. And there's planets and there's full-fledged stars. What's the difference? A star has its core get hot enough to fuse via the proton-proton chain, or as we'll see, the CNO cycle, full-fledged proton-based fusion. A brown dwarf's core never gets hot enough for that, but it does get hot enough to fuse deuterium for a while. So that's what makes it sort of a brown dwarf, is it is able to fuse deuterium, but it doesn't last very long because deuterium is a rare isotope. And planets are things which never get hot enough to fuse even deuterium. So why is Jupiter not a brown dwarf? Because it's not hot enough in its core to fuse deuterium. If you get about 13 times the mass of Jupiter, the core can fuse deuterium for a while. If you get to 80 times the mass of Jupiter, you can get full-on proton-proton chain, and you get a star. So brown dwarfs are objects between 13 and 80 Jupiter masses, where their cores get hot enough to fuse deuterium, but not hot enough to start the full proton-proton chain. Fun facts, okay? Let's complete the reactions here, and then that'll get us going for the next time, because I can't stop here. So then the next step is 21H, in other words, deuterium, plus 11H, a proton, fuse to form 3,2He. It's helium because there's 2 protons, but there's also a neutron, 3 total particles. Plus, what's that? It's not the Lorentz factor. It's a ray. It's a gamma ray. That's a gamma ray. Yep, that's a gamma ray photon. Because the helium-3 has less mass than the deuteron plus the proton, and that mass is converted into the energy of the gamma ray. In other words, that extra binding energy shows up in terms of it allows the gamma ray to be emitted. How long does this take? The answer is a few seconds. So in other words, once that deuterium forms, that's only going to last a couple of seconds. It very quickly makes a helium-3. That's almost instantaneous. And then the last step is 2 helium-3s, which were generated by the first 2 reactions. Helium-3 plus helium-3 becomes helium-4, 4,2He, plus 2 protons, 2 11H. In other words, in this last step, notice that there are 1, 2, 3, 4 protons going in, but only 2 of them end up in the helium-4 nucleus, and the other 2 fly out. They're released. And so that's why there's plus 2 11H there. And so notice then that the net reaction is that we've got 6 protons going in, right? 1, 2, 3, 4, 5, 6 protons go in. Yeah, 6 protons go in, but I'm getting myself confused. I'll say it next time. I'm confusing myself. Anyway, the net reaction, I could easily figure it out, but we're already past time, so I'll just shut up and say it smarter next time. 400,000 years is how long, on average, a helium-3 lasts before it hits another helium-3 and does this last stage. And so the net reaction, the overall reaction, is, and this is where we'll stop, 4 protons become a single helium-4 nucleus plus 2 positrons, right? Because there's one on this branch, there's one on this branch, plus 2 electron neutrinos, 2 nu E, plus 2 gamma rays. And these 2's here are again because there's 2 branches. The 2 helium-3s each were associated with the creation of a positron and a neutrino and a gamma ray. But the positrons aren't long for this world because the sun's full of electrons and the positron quickly meets an electron and they annihilate into a pair of gamma rays. So in practice then really you get 4 gamma rays out because 4 gamma rays out because the positrons are going to annihilate with electrons and make 2 gamma rays each. Okay, we'll stop there. Free education, I won't charge you any extra money for it. Yeah, right, it's just yes. 6 protons go in, 1, 2, 3, 4, 5, 6, but 2 of them fly back out. So in other words, it's 4 protons overall become the helium-4 nucleus, 2 of which turned into neutrons.